So let's consider how stars actually form. Stars form from really big clouds of gas and dust. So imagine we have this really big cloud and we get a fluctuation somewhere near the center where we have a slightly more dense patch in that cloud. Now that dense patch exerts a gravitational force on the rest of the gas and the dust in the cloud according to Newton's law of universal gravitation, F is equal to G m1 m2 on r squared. So that more dense patch is attracting the rest of the gas and dust in the cloud. So they all coalesce down. Now this actually happens adiabatically because the cloud is not losing energy to the surroundings. So we've seen that for adiabatic compressions we have the equation PV to the gamma is constant, and we can actually rearrange this with the ideal gas law to write it in the format T to the gamma over P to the gamma minus 1 is a constant. So what this equation tells us is that as the gas cloud is collapsing down, the pressure is increasing, and so the temperature must also be increasing. So our gas cloud continues to compress, it gets really hot, it gets really dense, and at some point there's enough energy there for thermonuclear reactions to start taking place. So at this point we start undergoing, depending on the mass of the star involved, which is going to be formed, the total amount of mass in the gas cloud, which is collapsing, we have proton-proton chain reactions or another form of chain reaction going on. So we have nuclear reactions going on. The nuclear reactions are producing radiation and particles which move out from the core of the cloud. As they move out, they're exerting a radiation pressure. So we've got two things going on. We've got the weight force collapsing the gas cloud down, and we've got the radiation pressure pushing the gas cloud out. When these two forces are balanced, then we've got an equilibrium reached. So our sun has reached such an equilibrium now, and it will stay stable until it runs out of the hydrogen which it's burning in its core. So by run out, we don't mean that there's no hydrogen left, we just mean that the density of the hydrogen is low enough that we're not getting enough of these nuclear reactions taking place to balance the weight force of the sun's mass. So when this happens, when the sun does run out of the hydrogen that it's burning, the weight force will win out and the sun will collapse down to a smaller volume. Now at some point for our sun, it's going to reach a temperature where there's enough energy for it to start burning helium and undergoing a different type of nuclear fusion process. So at this point, we'll once again have a flash as energy is released from the core, and the sun will actually expand outwards as the radiation pressure acts outwards, and we'll end up with a red giant. It'll stay as a red giant until it's finished burning all its helium, at which point it will collapse and become a white dwarf as it slowly cools. Now, the exact path followed depends on the mass of the stars involved. So we'll be looking at that in a little bit.